Hello. In this video we're going to talk about MOSFET amplifiers, or the use of MOSFET transistors in amplifier circuits. Small signal amplifiers is only one of the possible applications of MOSFET transistors. MOSFETs can also be used in other contexts, such as analog switches or in digital circuits to implement logic gates, digital memory circuits, etc. Now, for linear amplification, meaning to build a small signal amplifier, we are typically going to bias the MOSFET in the saturation region of operation. And just as a quick review, we have seen that there were three regions of operation for a MOSFET transistor. If we do a quick review of MOSFET operation, we'll remember that we had the cutoff region where the VGS voltage, let's imagine I have an NMOS transistor, which stands for N-channel MOS, with my three terminals, the drain, the source, and the gate. And so in the first region of operation, we had where my input voltage signal, my VGS, was less than some threshold voltage that was needed to induce a channel, basically to turn on the transistor. And therefore, we say the transistor is in the cutoff region of operation, or we also refer to the transistor as being off, meaning non-conductive. And so, in that region of operation, the current flowing through the drain or from drain to source was equal to 0. We can model a transistor which is biased in the cutoff region as an open switch or an open circuit, for example, something that prevents the flow of current. If we keep increasing our gate voltage, our input signal, that VGS, we may reach a point where VGS exceeds the threshold voltage, and then a channel is induced. And so I'll put that as 2 VGS is greater than my threshold voltage, assuming I'm talking about an enhancement MOS type of device. And so once that happens, again, I have a channel that is induced. We say the transistor is on. It can conduct current, and how much current it conducts, or how the current that flows through the transistor operates is governed by the condition applied at the drain, the voltage between drain and source. If the voltage from drain to source is less than the overdrive voltage, meaning the overdrive voltage will be precisely the difference between VGS and the threshold voltage, or how much the input voltage, the gate voltage, goes beyond the threshold voltage. And so if VDS is less than the overdrive voltage, then we have that the transistor is operating in the triode region, where the current depends on the output current ID, depends on the value of the output voltage VDS. A quasi-linear dependency there, so we can model the transistor as a resistor. That's why we call that the triode region. And so we saw that ID, we came up with a model for ID that said was equal to Kn, the transconductance parameter, times the overdrive voltage minus 1/2 of VDS times VDS. And so in essence, we can model that as a resistor. RDS, from drain to source. And so there's, again, if we were representing it in the family of curves, if we were to plot ID versus VDS, in the triode region, we saw that the current increases as VDS increases. And I guess I didn't put the name of it, but that will be the triode region. Sometimes you will see it referred to as the linear region. I'm going to try to avoid the reference to the linear region, because in linear applications we use the MOSFET in the saturation region, and so I don't want there to be a confusion between what typically is known as a triode or linear region and the region that we use the transistor in for linear amplification applications. So I will always refer to this as the triode region. And then finally, it could be that VDS is greater than the overdrive voltage. And in that case, we saw that there is a quadratic relationship between ID and the output voltage VDS, given by ID equals 1/2 of Kn times the overdrive voltage squared. And again, the overdrive voltage is VGS minus VT, and so there is a relationship between ID, the output current, and VGS, the input voltage. And in that case, we model the transistor as a current source because the current becomes constant with further increases in VDS. And so the model for that will be that of a current source where current flows from drain to source. That will be ID. And this will also be drain and source terminals, drain and source terminals. All right. Notice that I have used the parameter Kn, and that parameter is the MOSFET transconductance parameter, if you recall, and its value was equal to mu n, which is the mobility, in this case, of the N-type carriers, because I'm talking about an NMOS transistor, times Cox, which is the capacitance of the oxide per unit area, times the aspect ratio, the width over the length of the transistor. So the first part of Kn, that mu n Cox, depends on process. There are parameters dependent on process, and then width over length is the aspect ratio. It depends on the geometry of the device, and when you're doing discrete circuit design, you won't have control over it because you're using a transistor which has already been manufactured and packaged, and so it comes with the geometric dimensions that it comes with. But when you're doing integrated circuit design, you do have some room or the ability to design that aspect ratio. All right. And so those will be the three regions of operation. I didn't label the saturation. I'm going to redraw the family of curves of output current ID versus output voltage VDS so that we can clearly see the three regions of operation. In one case, we will have the cutoff region of operation, where the current is equal to 0. And then for all other cases, I will have my triode region of operation. So I'll put it in a more distinct color. My triode region of operation. So as my VGS is greater than the threshold voltage, so the transistor is on, but VDS, the output voltage, is not yet strong enough to put the transistor in saturation. It hasn't reached the overdrive voltage. And so we can see that for different values of VDS, our ID will be increasing in a quasi-linear fashion. And then finally we will enter saturation, where the current becomes approximately constant. Not quite, because as we have seen, there is the channel length modulation effect, and so there is actually a bit of a slope there because of the non-infinite output resistance of the transistor. And so I can draw a family of curves corresponding to different values of VGS, increasing values of VGS. I'm only going to draw 3 of them. There is this curve, which basically represents that transition. Maybe in this one, I would want to modify it a little bit so it fits our picture, because that black line will represent the transition between the triode region and the saturation region. And so that line will correspond to the case where VDS is exactly equal to the overdrive voltage, VGS minus VT. Okay. Again, this will be for increasing values of VGS or increasing values of the overdrive voltage. As we increase VGS, obviously the overdrive voltage goes up. And I guess the last thing is just to label this as my triode region and this as my saturation region. So that's a little bit of a review of the different modes of operation. Again, the different conditions for cutoff, I'll probably do this in yellow, for cutoff, triode, and saturation are specified here. So VGS, less than VT, we're in cutoff. If it is greater than VT, as long as VDS is less than the overdrive voltage, we're in triode. When VDS becomes greater than the overdrive voltage, we are in saturation. And so, as we mentioned, and as the slide says, for linear amplification operations, we're typically going to be in the saturation region. Now, just like with any small signal amplifier, and that's what we're going to be using the MOSFET for, the principle of operation is very simple. We apply a very small change at the input of the amplifier, and we get a large change at the output. And so if we apply a small, hopefully, change at the input, we get a proportional change at the output. And so if it is larger, we have achieved some gain. And so in this case, a small change in VGS voltage, we will see produces a large change in ID current or drain current. Now, since the transistor is a three-terminal device, there are three possible configurations that we can have for our amplifiers based on where we apply our common signal, our ground signal. And so we have the common source amplifier, common drain amplifier, and common gate amplifier. And again, it's simple. For the common source, the source is the common signal, and so the input is applied at the gate. And when we say the source is the common signal, typically referred to as, that's the AC ground, the ground for small AC signals. And so it doesn't have to be necessarily tied to ground in a circuit, but it should be tied to typically a DC level. So the AC level doesn't change, even though, as we will say, in some configurations that isn't always the case. But as a general principle, it works. So for a common source, the source is the common terminal, input applied at the gate, output taken at the drain. So common source. Our circuit will look like this for an MOS transistor. This will be the input, this will be the output. If it looks like this will be a common source circuit. Again, normally we assume that the source is the common terminal in that case. In a common drain amplifier, the drain is the common terminal, and so we will have our input applied at the gate and our output taken at the source. Now I've tied the source to ground, but that's incorrect. Normally that wouldn't be tied to ground. It will at least be connected, to ground through a resistor. But that will be where our output will be taken, the out. This is the terminal that is going to be typically tied to the common or ground, and then the common gate typically will look something like this, where the input is applied at the source and the output is taken at the drain. So this is more or less just a graphical way of visualizing what type of amplifier we're dealing with. We need to look at where the input is being applied and where the output is being taken off. Now, different configurations have different pros and different cons, and so we're going to see how they have different characteristics. Some of them are going to have higher gain, and so they're suitable for a gain stage. Some of them are going to have higher input resistance, lower output resistance. And so the idea is that we can, based on the characteristics of the different configurations, we can combine these amplifiers in what we call multi-stage amplifiers, and so basically attach them one stage to another in order to come up with an overall amplifier that will have ideal characteristics. Now, when we combine these in different stages, we need to account for the fact that there may be loading effects if the output resistance of one stage and the input resistance of the subsequent stage don't meet the corresponding relationships. And so there may be some loading effects which we can account for just by calculating the corresponding loading factors and keeping them in mind for our calculations. So here are the three configurations: common source, common drain, and common gates. Notice that this is representing the AC equivalent circuit, the small signal AC equivalent circuit. And so you don't see any DC sources being applied at the circuit. They have been replaced with either a short circuit to ground or an open circuit if you're dealing with a DC current source. And that's why you don't see any DC sources. These circuits, if you just connect them like this, obviously wouldn't work because they don't have any power, they don't have any DC supplies, and so the transistors are not even biased in the right region of operation. But this is a good representation of the AC equivalent circuits for a common source, common drain, and common gate amplifier. We mentioned in one of the videos last week that when we are analyzing or designing MOSFET amplifiers, we're going to use the principle of superposition, which basically entails we're going to split our analysis into a DC portion and an AC portion. And then we're going to apply superposition by saying the overall response of the amplifier, the overall output signal, is equal to the response to the DC stimuli plus the response to the AC stimuli. So basically we are representing all our signals based on their instantaneous values or overall values at any point in time. Let's imagine VGS, which we are going to represent as lowercase letter and then uppercase subscript. And every single one of them is going to have a DC component, which will represent with uppercase letter, uppercase subscript, and an AC component, which we are representing by lowercase letter, lowercase subscript. And that applies to everything. Same thing with, let's say drain current is going to be ID. The DC portion, which represents the value, the Q point or quiescent drain current, plus the small signal AC portion, which represents the change in AC current as we apply a small change in the input signal. And so typically, again, the first part will be the DC component. The second part will be the small signal AC component. And so when we are analyzing our circuits, we're going to be very typically taking the overall circuit, and when we're doing the DC analysis, just drawing our DC equivalent circuit. And what do I mean by a DC equivalent circuit? Well, it's a circuit where I have turned off all the AC sources and I've only kept the DC sources and or the DC models for the circuit components. So if I have some capacitors that I know they behave as open circuits for DC signals, then I'll replace those with open circuits, etc. That will be my DC equivalent circuit. And all the signals in my DC equivalent circuit should be DC signals. I will always represent them as capital letter, capital subscript. And then when I'm doing the small signal AC analysis for my circuit, I'm going to do the opposite of that. I'm going to turn off all my DC sources in order to come up with my AC equivalent circuit, in which only the AC sources are being considered, and typically circuit components will be replaced with their AC equivalent, etc. And all the signals, when I label them in the AC equivalent circuit, are going to be labeled as lowercase letter, lowercase subscript, indicating I'm just dealing with the small signal AC component for those signals. Now, when we're performing the small signal AC analysis, sometimes it is useful to replace the transistor with its small signal equivalent model. And up here you have representations of two versions for that model. They're equivalent representations, meaning they both represent the behavior or model the behavior of the transistor for small AC signals. The reason why you will use one or the other is because sometimes the use of one or the other simplifies your analysis, but other than that, they both should give you the same result. The hybrid pi model, again, the transistor is represented as a current source from drain to source, and then as an open circuit from gate to source, because there is an open circuit there is no current flow because of that oxide layer at the gate. So you have a VGS voltage applied at the input. Notice the lowercase nomenclature for the signals, because we're dealing with small AC signals now. And then your output current is proportional to the small signal input, VGS, and the proportionality constant is the small signal transconductance, GM. Because transconductance indicates, the ratio of an output current to an input voltage. That is exactly what we have here. And in this case, we have modeled that output resistance, little r(O). You can assume it is infinity, but you can model it if you want to have a more accurate model. That's related to the channel length modulation effect and how, even after you enter saturation, the drain current increases slightly with increases in drain voltage. And it's modeled with a parameter represented by the Greek letter lambda that we have seen has a unit of inverse of volt. And then the T model, it has, it's pretty much the same thing, except in here we represent a small resistance here of value 1 over Gm, 1 over the transconductance. And it can be shown that both circuits are equivalent to each other. And again, all you will do when you're doing your small signal AC circuit, you will just replace your transistor with whichever one of those two models you have selected, and it should help your analysis of the circuit. We looked at the small signal parameters and how to calculate those already. There are only two parameters to calculate for the model of a MOSFET. That is GM and little r(O) if you are taking into account little r(O). GM is transconductance, and so is rate of change of output current, ID, with respect to rate of change of input voltage, VGS. And so when you write down the equation for the drain current in saturation and you take the derivative with respect to VGS, you calculate the transconductance. And there were three different expressions from it. And the reason why we came up with three different expressions is because each one of them may be suitable in a particular scenario. We saw that even though the three expressions are equivalent, they're written here. In one of them, Gm equals Kn times the overdrive voltage, VGS minus VT. We have an expression of transconductance which is independent of drain current. In the second case, Gm equals the square root of 2Kn times the drain current. We have an expression for the transconductance that is independent of VGS, or the input voltage. It only depends on the current and the process parameters, basically, the MOSFET transconductance parameter. And in the third case, Gm equals 2ID over the overdrive voltage. We have an expression for Gm that is exclusively dependent on the DC bias points, ID and VGS, or ID and the overdrive voltage. There is no transconductance parameter, no process parameters. And so you can calculate Gm even if you're missing one of those pieces of information. And then if we take into account channel length modulation, like I said, we need to expand a little bit our expression for ID, where it is no longer just 1/2 of Kn times the overdrive voltage square, but there is an additional term, which is times 1 plus lambda times VDS, lambda being the channel length modulation parameter, and that models the dependency between ID and VDS, meaning the output current and the output voltage, for the MOSFET transistor in the saturation region. And whenever you have a changing output voltage with a link to a changing output current, that means that you have an output resistance. And so if you want to calculate your output resistance, if you calculate the rate of change of current with respect to voltage, that will have units of conductance, not resistance. And so if you take the inverse of that, the inverse of the output conductance will give you the output resistance. And if you apply that to the equation, you get that it is equal to 1 over lambda times VDS, or if you want to write it in terms of the early voltage, which is the equivalent parameter that we use to model the output resistance in the BJT transistor, it will just be the early voltage divided by ID. And so you can sort of say, the equivalent of lambda will be that it is equal to 1 over the early voltage. And finally, how, just as a quick review, how do we use the MOSFET as an amplifier in a particular situation? Out here we have a common source amplifier circuit. Notice that there is a lot more components connected around that transistor than simply just applying an input signal to the gate and taking the output signal out of the drain, as we expect for a common source amplifier. And the reason for that is that before we can perform a small AC amplification, we need to bias the transistor, provide a DC bias into the right region of operation. And that's what a lot of these components are doing. And so you have some resistor network around the transistor, which is basically setting the Q point, meaning we have all these families of curves, and we want to put the transistor operating at some point. I'm going to draw it here in case you see it better, which we're going to call the quiescent point. And so the idea is that's going to place the transistor in saturation, which is the right region for linear amplification. And now once I am in saturation, I can apply a small change to the input signal, which is going to produce changes around that Q point, around that quiescent point, but I'm still going to be in saturation. Specifically, I can provide a change in VGS, meaning my VGS goes up and down, so that will be my small signal VGS. It will go up and down around the Q point, and what that will imply is that the transistor will be moving, between curves, and hopefully, it wouldn't move this much because my VGS change is not that great. But you get the picture. The ID will also be changing, and so essentially we will be moving the transistor between, say, one point and another. Along those lines, and so the values of the currents, voltages, etc. in the circuit will be all moving around that quiescent bias point. So those resistors R1, R2, RD, they're here to set the quiescent bias point. Once that is set, we apply a small AC signal to the gate of the transistor because we're in a common source amplifier. Notice that we apply the signal through a capacitor CC, that's a coupling capacitor, and the reason why that is there is because typically my signal is going to have either no DC offset or a DC offset which is different from whatever DC value I set at the gate of my transistor in order to set the DC bias point. And so I don't want the DC value of my input signal to interfere with my DC bias point. If this signal is centered around 0 volts and my gate is set at a DC bias point of, say, 3 volts, I don't want those two DC values interfering with each other, and so I place a coupling capacitor. That way I decouple my signal. I only let through the AC portion of the signal, and so I don't disrupt my DC bias point at the gate of the transistor. So I applied my input signal. Again, it's a small changing input signal. basically creates, since my source is tied to ground, if I apply a small change, let's say a small increase in my gate voltage, that corresponds to a small increase in VGS. So notice a small increase in VGS, a small signal VGS. Since VGS is related to the drain current through that square relationship, if I increase VGS, then my drain current also increases. And if my drain current increases, my voltage drop across resistor RD is going to increase, which means my output voltage is going to decrease, because my output voltage is VDD minus the voltage drop across RD. So if the voltage drop across RD is larger, then Vout corresponds to a lower voltage. And so that's how an increase in input voltage gives me an increase in output current, which gives me a decrease in output voltage. Because of the opposing nature of the change in input voltage and output voltage, we say we have an inverting voltage amplifier, where the gain of the amplifier is going to be equal to negative Vout over Vin. And notice these are small signals, so this will be the change in Vout over the change in Vin, not taking into account the DC portions. And that's it for the review. Perhaps one last thing to mention is that as we design these MOSFET amplifiers, it's going to be helpful to look at them from a macro model point of view, voltage amplifier macro model. What do I mean? Well, we're going to be facing circuits that have transistors, have resistors, have capacitors, have a lot of components. And it's easier to consider these circuits, especially as we start building multi-stage amplifiers, to look at them based on a simplified model. We have different voltage amplifiers. All these different voltage amplifiers are going to have some gain factor. The gain is going to give me the relationship between the input signal and the output signal, which is great. And then the only other piece of information that I need is how are these amplifiers going to interact with each other when I connect them together. And that's given by the input-output characteristics, or the input resistance and output resistance. So whenever we analyze or design amplifier circuits, we're going to use a two-port network amplifier model, basically looking at the amplifier as opposed to keeping in mind all these transistors, all these resistors, all these components. We're going to calculate the model parameters, gain, input resistance, output resistance, and then we're going to proceed with our analysis and design and combining stages together by simply using this model, okay, of the amplifier. It's going to simplify things a lot, as we have seen for the BJT, but as we will see as well for the MOSFET. And that's it. We are ready to start analyzing and designing MOSFET amplifiers.